In this lecture, we're going to be taking a look at a new way to measure an angle using something called radians. In the last lecture, we talked about measuring degrees, and now we're going to talk about radians. Radians is a nice new type of measurement that makes it much easier to work with circles, which is going to be a very central part of what we do in trigonometry. To begin with, let's define the concept of a central angle. Now, central angle basically means any angle where the intersection of the terminal and starting or initial side is at the center of a circle. So a central angle is a positive angle whose vertex is the center of a circle. When the rays intersect the circle, it creates this arc out here. Okay, that's what we're going to call an arc. Okay. Now, when the arc created by the central angle, so we've got an angle here of a certain measure, if the arc length, that is the distance along this arc, is the same as the radius of a circle, then that particular angle is going to be a measure of 1 radian. Okay, so again, we took the length of the radius and we stretched it along the outside and we create an angle that goes through those two endpoints. That angle measure is 1 radian. Now, the nice thing about using this as the measure of an angle is that you can actually come up with a pretty simple formula for how far along the outside you travel if you happen to know the measure of an angle in radians. Okay. So if you've got a circle of radius r, like we have here, and we know some angle inside there, let's say we don't know that it's 1 radian, let's say it's just any angle. Okay, so you've got some circle, you've got some angle, and you know that the angle here is theta, but instead of theta being given in degrees, it's given in radians. Okay? Well, if it was 1 radian, you know that the length along the outside was the radius of the circle. If it was 2 radians, you would know that you would travel 2 of those distances of the radius, so you'd be 2r, or 2 times the radius of the circle. And if you actually had theta was any number, you could find out what the arc length s would be by taking the radius of the circle times whatever your angle measure is in radians. So S is equal to r theta. Okay? So if you know the angle measure in radians, you can easily find the arc length with that formula right there. So here's a quick example. If you have a arc length of a circle and you want to find out what that is, and you know that the radius is 2, so r is equal to 2, and you have the measure of theta. Theta is 0.25, that is, it is 0.25 radians. Then you can find the length of the arc by simply taking 2 times 0.25, just from this formula right here, and you get 0.5. And since the radius was in meters, your distance along the outside is 0.5 meters. One of the first things we can comment on is the fact that we actually know how far it is, that is 1 complete revolution, how many radians that is. We know that's 360 degrees, but if you take a circle, let's say we take a circle, the simplest of all circles, that has a unit radius. Okay, what's the distance around the outside? What's called the circumference, right? And we know that the circumference of a circle is always 2 pi r, so in this case that distance around is 2 pi. And since we know that s is equal to r theta, s being the arc length, if I were to start here and go 1 complete revolution and end up where I started, then my distance around, which I know is 2 pi, should also be equal to my radian measure times my radius. So in this case, my 1 revolution is going to be 2 pi radians, because the distance around is 2 pi, that's the s. This r right here is 1, so theta has to be 2 pi, that's the distance all the way around. So in other words, 360 degrees is equal to 2 pi radians, or if I divided both sides of that equation by 2, I have this relationship right here, that pi radians is 180 degrees. Okay? Now, let's say, for example, that I wanted to convert from degrees to radians. That means I need to know how many radians there are in every degree. So if I take this equation right here and divide 180 to the other side, I end up with 1 degree, right? I had 180 degrees divided by 180. I got 1 degree is equal to pi over 180 radians, which means that in order to convert from degrees to radians, all I got to do is multiply by pi over 180. On the other hand, if I took the pi and moved it to the other side, divide it across, I would have that 1 radian is equal to 180 degrees over pi. So multiply by 180 over pi if I want to convert the other direction. Okay, and I'll show you a quick and easy way to remember which one you multiply by, because you're either going to do pi over 180 or 180 over pi. Now, one of the things that you'll notice is that in general, just most often in this class, when we talk about radians, you'll tend to see a pi show up in the measure. Okay, it's a very common number that shows up in all of our values for radians. Not necessarily. I mean, I can talk about 1.25 radians. We've already seen 0.25 radians. But for the most part, what you will see more common is actually pi over 3, pi over 6, 2 pi over 3, pi over 5. You'll see different measurements that contain that pi. And so when I see something like 60 degrees, if I want to convert that to radians, then I want the answer to probably have a pi in it. So I'm going to actually use pi over 180. Or I just remember the fact that if I'm going to go from degrees to radians, I multiply by pi over 180. Now what happens when I do that? Think of 60 as a fraction. You can cross cancel, meaning that you can divide a 60 out of both of those and end up with just pi over 3. So 60 degrees is a third of pi, or pi over 3 radians. If I wanted to convert 150 degrees, I could do that by taking, again, multiplying by pi over 180. In this case, I can divide a 30 out of the top and bottom to reduce that fraction. That gives me, if I take 30 out of this, gives me a 5. If I take 30 out of this, gives me 6. So I get 5 pi over 6. That measurement right there is the same as 150 degrees. Now, hopefully, by the end of this chapter, or this section, before we start talking about trig functions, you're going to want to become familiar enough to look at 5 pi over 6 and immediately recognize that that's an angle of about this size right here. Okay, 150 degrees, not quite to 180. Pi over 3 is a 60 degree angle. Okay, something of that size. All right, what about negative 45 degrees? What happens when they have a negative? Well, clearly you're still going to multiply pi over 180, but now because it's negative, you're going to end up with a negative number of radians. In this case, 45 goes into 184 times, so you end up with negative pi over 4 radians. And last of all, let's do 90 times pi over 180. 90 goes into 180 twice, so you end up with pi over 2. I got one more. We'll go to the next one. All right, so last one, 107 degrees multiplied by pi over 180. Now in this case, 107 does not divide or simplify when you divide it by 180, so you actually end up with 107 pi over 180, which, as you'll see, one of the things we'll do is we'll reduce when we can. If we have one that's not one of our special families of angles, pi over 6s or pi over 4s or pi over 2s, we will typically ask you to, in homework exercises, to go ahead and round this. So let's round this to the nearest hundred. So this is 1.87 in radians. So let's take a look at our circle here and fill in what the different radian measures are going to be for all of our different angles. So to begin with, 0 degrees is going to be 0 radians as well. We've already seen that 1 full rotation is pi. Half a rotation is 180 degrees, but that's also going to be just pi, which you can get all of these by multiplying these by pi over 180 and then reducing the fraction. But another way to get there is to basically recognize some of the families of angles that you have here. For example, 90 degrees, we already saw on the previous page, is pi over 2. So if that's pi over 2, you add another pi over 2 to that, you get 2 pi over 2, which is just pi. Add another pi over 2 to that, you're going to get 3 pi divided by 2. Okay, so 270 is 3 pi over 2. So 0, pi over 2, pi, 3 pi over 2. Those are your quadrantal angles, or your axis angles, right? 45 degrees we saw was pi over 4. Okay, so if you take pi over 4, 2 of those is going to be pi over 2. Pi over 4 is 45. 45 together again is 90. Okay, but if you add another pi over 4 to that, you actually get 3 pi over 4. Since this is 1 pi over 4, 2 pi over 4, 3 pi over 4, and then here's 4 pi over 4, which reduces to pi. Okay, and then you got 5 pi over 4 down here, and 6 pi over 4, and then 7 pi over 4. Of course, this would be 8 pi over 4, or 2 pi, but also can be written as 0. Then you can do the same thing with, say, 60 degrees. 60 degrees is pi over 6. Okay, so 2 of those would be 120 degrees, which is 2 pi over 6. So not 6, I meant 3. I'm sorry, let me erase that and write the 3 that I meant to say and write. That's pi over 3, and then 2 of those is 2 pi over 3, and then 3 of those would be 3 pi over 3. So 60, 120, 180, 3 pi over 3 is pi. Okay, add another pi over 3, you're down here at 240, that's going to be 4 pi over 3, 4. And then you got 5 pi over 3, and then 6 pi over 3, which is 2 pi, or 0. Now 30 degrees is going to end up being pi over 6 when you multiply it by pi over 180. Okay, so adding 30 degrees at a time is going to get me 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, and then down here is 5 pi over 6, 6 pi over 6, 7 pi over 6. Notice 8 pi over 6 we already have because that reduces to 4 pi over 3, 9 pi over 6, 10 pi over 6, and then 11 pi over 6 is the only one that we have left. And so these are the most commonly seen angles, and you should recognize this, and I think it's going to be good practice for you to fill in these blanks regularly just so that you remember where these different angles fall on the circle. Now, just like we can convert from degrees to radians, we can go back the other direction. Remember that to convert from radians back to degrees, radians to degrees means we multiply by 180 over pi. The way that I remember that is that I'm trying to cancel out the pi that appears in the radians, so the pi needs to be on the denominator. So to convert pi over 6 radians to degrees, I would take pi over 6 times 180 degrees over pi radians. The pi's cancel, and you're left with 180 over 6. 180 divided by 6 is 30 degrees, which matches what we saw in the above table. To convert 3 pi over 2 directly is to multiply by 180 over pi. The pi's divide out. 2 goes into 180 90 times. 3 times 90 is 270 degrees. If we wanted to convert negative 3 pi over 4 to degrees, we'll multiply by 180 degrees over pi. The pi's divide out. 4 goes into 180 45 times, and 3 times 45 is 135, and the negative carries through, so you have a negative 135 degrees. 7 pi over 3, done similarly, multiply by 180, divided by pi. The pi's divide out. 3 goes into 180 60 times. 7 times 60 is 420 degrees. Okay, which, by the way, is equivalent, if you were to take 420 minus 360, then you would get let me erase that question mark. Equivalent in terms of what the angle looks like on the coordinate plane, okay, that would be equivalent to a 60-degree angle, right? Because 420 minus 360 is 60. Okay. However, I want you to go ahead and write that answer, because if you remember what angles mean, they actually mean the amount of rotation it takes to get from one place to another. If I were to say that a car spins around 420 degrees or a car spins around 60 degrees, the car has done two different things, right? 420 degrees, it went all the way around once plus another 60 degrees. If a car turns around 60 degrees, it just turns 60 degrees, okay? So two different actions are happening. So we can describe those things differently, even though they look the same on the coordinate plane, okay? 3 radians, in this case you don't have any pi's, but you'll still have to multiply by 180 divided by pi, okay? Which gives me 540 divided by pi, which I'm going to plug into my calculator. Now, most of your calculators will actually have a pi key that will type in the number pi, but you can approximate it if you don't have that by simply dividing by 3.14. 540 divided by 3.14 gives me 171.9 degrees. We've already seen that whenever we have the measure of an angle in radians, we can calculate arc length using a formula S is equal to r theta. And the source of that formula is simply the concept, the understanding of what radians actually mean. As long as theta is in radians, then to multiply the number of radians of the angle by the radius of the circle will give me the distance along the outside. Well, another feature of the definition of radians is that we can find the area of a sector. So whereas the arc length was the distance along the outside, the area is going to be this area inside that sector. Now we know that the area of a circle is pi r squared. Okay? So what happens with this is that if you were to take half a circle, you actually end up with pi r squared over 2. In fact, this can be used to calculate whatever the full circle is. If you divide it in half, you can get half of the circle. In fact, you can use this to get any proportion of the circle. Okay? But theta actually tells you what proportion of the circle, where this right here is not theta, but actually half of theta. That is, the number that's right here in front of the r is not theta, but theta divided by 2, right? Because pi is half of the circle, but if you went all the way around, so you have a circle and you went all the way around inside, right, you'd have the whole area of the circle. If you took the full rotation, that's 2 pi, and divided by 2, you get pi, okay? So the formula for the area of a sector is always going to be theta which is the number of radians. You take half of that and you do r squared. 1/2 theta r squared. Okay? In other words, if we know the angle in radians, we can find the area of the sector. So let's find the area of a sector whose circle has a radius of 2 feet and is formed by an angle of 30 degrees. Note, 30 degrees must first be converted into radians. So remember, you multiply by pi divided by 180, which is going to give me, when it divides out, 30 goes in 186 times, so I get pi over 6. So using this formula above for the area of a sector, you take 1/2 times pi divided by 6 times the radius squared, 2 squared. All right, so 2 squared is 4. 4 times this half out front is 2. So you have 2 times pi over 6, or pi over 3 square feet, or approximately 1.05. I lost my pen. Where are you? 1.05 square feet. Now, the last thing that I want to do is show you another application, one-third a third application of using radians. So we've talked about finding the arc length. We've talked about finding the area of a sector. We can also now talk about the difference between an object that moves in a circle and an object that moves in a straight line, and talk about the comparison of their angular speed versus linear speed. So first of all, what do we mean by angular speed and linear speed? Let's define linear speed first. Suppose an object moves around a circle of radius r at a constant speed. If s is the distance traveled, then the linear speed, that is the actual speed that they're moving in the direction that they're moving, is v is equal to s over t, right? That's velocity. V stands for velocity, is distance over time, right? So if you're traveling in miles and your time is in hours, that's miles per hour. Okay, that's time on bottom, that's length on top. Now what we mean by angular velocity or angular speed is how fast in terms of radians are we traveling. So where theta is measured in radians covered in time. So this is like radians per unit time, which would be radians per second, radians per minute, radians per second. And we can use this formula to simply convert from angular speed to linear speed. Okay? Another way of measuring angular speed is to also do something called rotations per, say, minute, for example. You've probably heard of RPMs. That is an angular speed, how many rotations we're going around per minute. Okay? But that's actually equivalent to 2 pi radians per minute. Because if you'll remember, 2 pi is the number of radians in one rotation. So if you had rotations per minute, you could actually convert that real quickly to radians per minute. But now using the fact that we know that s, that is the distance traveled, is equal to r theta, if we just stick this theta in here, then it turns out that v is the same thing as r times theta over t, but theta over t from right here is w. So r w, or r, I think omega is what the book actually types in there. Okay, so the point being that if you know the velocity in linear speed, then you can find, let me say that backwards. If you know the angular speed, so if you know rotations per minute or you know radians per minute, you can convert that to linear speed using this formula right here, or this one right here. Okay? So let's say we got a child spinning a rock at the end of a 2-foot rope. So we've got a 2-foot rope, and there's a rock tied to the end of it, and it's going around in a circle. Okay? And we know it's going 180 rotations per minute. So they're spinning this thing out at a speed, so it goes around the circle 180 times every minute. The question is, how fast is that rock traveling on the end of that string? Okay? Well, I'm going to use this formula, but first thing I got to know is what's the angular speed. Okay? How many radians per minute? Okay? What we already know is 180 revolutions per minute, but I know that there is 2 pi radians in every revolution. So if I multiply those two together, I get 360 pi radians per minute. There's my W, or my omega. Linear speed is going to be RW, so that's going to be a 2-foot rope, because that's the radius, times W, which is 360 pi, or 720 pi feet per minute. Okay, that's, if you multiply that out, you get 2,261 feet per minute. Okay, I just multiplied 720 times pi. So you see what I did? I just took the Radius times the number of radians per minute. To get radians per minute, I took revolutions per minute times 2 pi, since there's 2 pi radians in every revolution. Okay, I really want to know how fast this is, so let me get a little bit more space down here. Sorry, you're running out of space on your page, but let's convert 2,261 feet per minute to miles per hour. So to convert to miles per hour, first let's convert the feet to miles. So remember that there are, in every mile, for 1 mile, there are 5,280 feet. All right, so that'll cancel my feet. That's why I put the feet on bottom. Now I want to convert the minutes to hours. All right, so how are minutes related to hours? All right, I put the minutes on top so it'll cancel with the minutes here. There are 60 minutes in 1 hour. If I multiply straight across and then divide by everything that's multiplied by on bottom, throwing that into my calculator, I get 25.7. I took 2,261 times 60 and then divided that all by 5,280 and got 25.7 miles per hour. Okay? And that's the end of lecture 6.